Yeah.
Yeah.
Just will introduce you. Just.
Yeah. Okay. At the start, I would like to introduce our guest speaker. So, Dr. Julian Steer. So, it's a great pleasure we have you to give us a talk. So, Dr. Julian Steer is originally from the chemistry industry, where he held roles in the new product development, scale up, and full-scale manufacturing of photo-imaginable polymers for circuit board coatings. And Julia is now based in the School of Engineering at the Cardiff University, where Julia gives some dynamics and carry out research on the themes of energy, waste, and the environment. In the last 10 years, Dr. Julian Steer has worked closely with the steel industry, carry out research on a range of topics, including hydrometallurgic and pyrometallurgic recovery of metals from process dust, alternative and novel both process modifications to increase the recovery of iron in dust, and the microwave analysis of particulates, and optimization and selection of coals for blast furnace coal injection, and build out and catalyst mechanisms to utilize industrial carbon dioxide production. Dr. Julia Steer is currently carrying out a project funded by the Sustain Network, collaborating with Tata Steel, N&P Recycling, and Swansea University, investigating the incorporation of paper and plastics as alternative reductants for the blast furnace process to reduce carbon dioxide emissions from ironmaking. Personally, I have known Julian for a number of years, and I would like to thank Julian to, in the past, support our PhD students to use his outstanding equipment. And now, Julia, the floor is yours.
Okay, thank you very much, Zushu.
Yeah.
Thank you. And first of all, thanks very much for the opportunity to speak today. It's a great chance for me, actually, to scrutinise CO2 emissions from the steelmaking industry, and in particular, what I'm going to talk about more specifically, the ironmaking process, because that's been a big part of my most recent research. So, as Zushu said, I'm currently funded by the Sustain Network, and I'm sure maybe all of you are aware of the Sustain Network, the Strategic University Steel Technology and Innovation Network, and looking at alternative reductants in the blast furnace with a view to reducing the CO2 emissions associated with the process. But firstly, before I start on the presentation proper, I think what's very clear is that this is an exciting time for the industry. It feels like there's a growing momentum to reduce greenhouse gases, both with government policy, targets, media coverage, public opinion, but also, very importantly, there's a lot of industrial activity now, and there's a growing amount of industrial activity and quite diverse activity. And that's what I'm going to try and cover for you today. And so hopefully this will be of relevance to all of you. Right, so firstly, what's the situation? And we can't obviously talk about iron production unless we talk about steel production. And world steel production has been increasing substantially over the last 20 years. So we've seen massive increases in world steel production, driven mainly in Southeast Asia, driven mainly by China, who have predominantly adopted the blast furnace, basic oxygen furnace route to making steel. In the UK, the UK's steel requirement is somewhere in the region of 20 million tons. So that works out per capita of about 300 kilograms per person. And what's quite striking is that the UK, buys a lot of that, imports a lot of that requirement in. Although we produce a total of around 7.3 million tonnes, about 5.6 million tonnes of that is from the blast furnace, and the remaining 1.7 million tonnes is from the electric arc furnace. Now, on the right-hand side, I've put a figure that just to kind of recap, really. I know many of you will be aware of the different routes for making iron and steel. We've got a couple of blast furnaces in the UK at Tata and British Steel. So on the left-hand side, you've got the blast furnace, which takes materials that require some pre-processing, so turning coal into coke, and then using that fine ore to produce a sinter product. Those raw materials then going into the iron making process, and then that goes into a basic oxygen furnace. On the right-hand side, we've got then the other end of the spectrum, which would be the recycled steel going into the electric arc furnace. And then in between, we've got other technologies, which, although are currently well developed, they're not always well used then. So we've got direct reduced iron, we've got shaft furnaces, rotary kiln furnaces, fluidized bed. We've got a range of different other production routes in between that blast furnace and the electric arc furnace. So what about worldwide production? Well, I guess what I want to emphasize in this slide is that, first of all, global crude steel production in 2019 was 1.8 billion tonnes. It's a massive amount of production there, and it's dominated by two technologies, really: the blast furnace and the electric arc furnace. The blast furnace itself takes up the majority. About 70% of global steel production is from the blast furnace. And that represents primary production, about 90% of the primary production. And so what we're referring to there is production from mined iron ore, iron oxide, or a variety of different iron oxides then. Then the electric arc furnace and the blast furnace combined account for 95% of all of the steel production. So it's dominated by these two real technologies, even though we've got other options open to us. And I think at this point, it's worth emphasizing that it looks like this situation is set for a big change now, because when we're considering reducing CO2 emissions, we're starting to look at some of these other technologies and combinations of those technologies. So where are we with the current situation with regard to CO2 emissions? So on the top left-hand side, I've got a table there from the International Energy Agency Iron and Steel Technology Roadmap. They produced a roadmap at the end of last year, actually. That kind of emphasizes where we're at, really, on terms of the specific intensity of CO2 per ton of hot metal. And there's some variation in the amount of CO2 that's produced per ton. As you'd imagine, there's a variety of different scales and efficiencies of plant around the world. But basically what we're emphasizing that is that the blast furnace has a higher specific intensity. So we're around a couple of tons of CO2 per ton of hot metal. Then the directly reduced iron, which might go into an electric arc furnace, then is less. And then the lowest of the current technologies which are adopted is the scrap-based electric arc furnace. So it's quite a considerable difference there at 0.3 tons CO2 per ton of hot metal out of that furnace. And in terms of global greenhouse gas emissions, iron and steel is a big part of 2.6 gigatons of CO2 emissions per year. So it produces a lot of emissions. And as a percent, it's usually represented as a percentage of the the energy sector of greenhouse gas emissions, and where it's 7.2% of those overall energy emissions, and then a lower percentage as a percentage of the total greenhouse gas emissions, which are around the 49 gigatons of CO2 equivalents per year. So it's a big producer. It's the #1 in the heavy industries, and this is all set against this background of global demand for steel increasing by more than a third up until 2050. And it's another thing that's worth emphasizing as well is that a lot of the growth in steel production in Southeast Asia is relatively young growth as well. So a lot of the production capacity is still quite young. So I think we've got a figure there of around 13 years of age on average. That's accounting for recent refurbishments. So it's going to be quite a challenge to move away from that current blast furnace in those regions then. So in terms of the energy, primary ore-based production is around 15 gigajoules per ton. So it's far and away, it represents far and away the most energy intensive of the processes. The scrap-based route is down at 2 gigajoules per ton. So significantly better, significantly lower energy requirement there. And then I've just put a figure of, just to put some perspective on that. Per ton, bread takes around 6 gigajoules per ton. And of course, that's quite a highly processed material. When it comes to energy, it's #2 among the heavy industries. And since 1960s up until the 1990s, there was quite a rapid decrease in the energy consumption per ton of crude steel production. But that rapid, the rate of that reduction now has slowed. It's not stagnated, but it's slowed. And you can see a lot of that energy associated with steel production is from coal, this coal-derived energy. So my talk is going to be split mainly into 2 parts. I'm going to look at the current blast furnace situation and opportunities there are to reduce emissions. And I'm going to reflect on some of my own work and some of the work that's been supported by Sustain. And then I'm going to look at the future direction of ironmaking and steelmaking. So we put some context in it and look at what other countries and what other suppliers and producers are looking at. So just going through the technology routes quickly again. We've got this blast furnace, and of course this high energy requirement and the CO2 emissions is a carbon-based thermochemical process. And it requires processing these raw materials quite significant before we charge them to the furnace, even before we start to use them. And of course, that results in this energy intensity. Then we have smelting reduction. Now, that hasn't got the pre-processing of producing coke and producing agglomerated fines in the form of sinter. And that also produces, like the blast furnace, also produces a liquid hot metal product, which tends to go into a basic oxygen furnace, tends to. Then we have the direct reduction, which uses iron ore directly with gases. They could be syngases or hydrogen possibly, or coke oven gas, depending on, and there are very well established technologies that are in place in the industry for producing directly reduced sponge iron. So in the solid form, it's a lower temperature. That's why the energy emissions associated with it are lower. It's a lower temperature, and it tends to be used to improve the quality of the final product from the electric arc furnace. And then, as we described previously, we've got scrap-derived steel production from the electric arc furnace. And we'll cover some of these in a little bit more detail later. So right, in terms of the blast furnace iron making, in terms of the energy balance, it's a very energy intensive process. It's, if ever you get the chance to see a blast furnace up in person, I really recommend it. These reactors, these thermochemical reactors, are some of the most grand pieces of engineering that you could ever imagine. They're massive. These are the biggest reactors in the world. Not always the cleanest of of reactors, but the process itself is fascinating, and it's a countercurrent heat mass exchanger. So solid raw materials, coke, iron ore, fluxes are charged at the top of the furnace, and then you've got a heated blast of air that's directed in from the bottom of the furnace. So the highest temperatures are at the bottom of the furnace. They're typically raceway adiabatic flame temperatures in the region of 2,200, and then at the top of the furnace you've got temperatures that are closer to 100, and most of the energy comes from this carbon-based coke or injected reductants, like I've been involved with, injected coal. So compared to the other technologies, the energy balance, specific energy then, gigajoules per ton, is highest for the blast furnace. So then, looking at producing steel, the iron containing a certain percentage, typically about 4% carbon, goes into the basic oxygen furnace, where that carbon is combusted off. And there are, overall, that route for making steel, most of the emissions are associated with iron making in the blast furnace. So I've circled that figure there of, I'm going to try and highlight this. So yeah, I've circled that figure there in the blast furnace of 1,200 kilograms of CO2 per ton of hot metal out of it. Now, Japan has the lowest global energy intensity of this route. But potentially, and this leads on to the evolution of the blast furnace, a lot of this exhaust carbon in the form of carbon monoxide, carbon dioxide, can be recycled through the process to be more completely utilized. And then as a material balance, the blast furnace, you're using around 2.4 tons of raw materials to produce a ton of crude steel. So it requires a lot of materials as well, compared to the electric arc furnace route, which doesn't require anywhere near the same quantity of raw materials. So historically, the developments that we've seen, the improvements that we've seen, have all been driven by scale, really. Blast furnaces have increased massively in size. And in fact, in 2016, POSCO, which is the Korean steel manufacturer, they started metal production using a blast furnace with an internal volume of 6,000 cubic meters, capable of an annual production of 5.65 million tons. So massive scale. And, it's an industry that's really improved its efficiency through scale, really. On the bottom left-hand side there, we've seen some real big improvements in the use, efficient use of raw materials in the blast furnace. Quite significant reductions. But as I mentioned earlier, the rate of the reduction in amount of material that is going into the blast furnace is kind of slowed down. We're approaching more the thermodynamic limits of the process. And then on the right-hand side, we've got technological developments which in comparison with the reduction in the equivalent of the coke rate, so quite significant reductions in the amount of coke that's going into the process. And that's been an important development in improving the efficiency of the blast furnace. So currently, what are the pressures on this route as a viable way of reducing CO2 emissions? So it's the greenhouse gas emissions that I emphasised. You know, it produces quite high specific greenhouse gas emissions. Its energy consumption is high. It's a carbon-based chemical reaction, thermochemical reaction. We're also seeing reductions in the availability of quality iron ores, and also the availability of lump ore. So we're seeing increases in the amount of iron ore fines. So that's an issue as well. And you know, ultimately, there's only a limited amount of iron ore that can be extracted from the earth anyway. So as a background into the industry and into the blast furnace itself. Now I'm going to look a little bit more specifically into some of the work that I've been done. Now I've been looking at injection coals. Now I must be quite honest that the push from the industry really is because coal injection is used to improve the efficiency of the blast furnace, so producing more for less materials. And it's been driven predominantly by this efficiency, the requirement to use different types of coals, coals that are economically more attractive. So the picture in the center shows the pipes which coming down, which are the hot blast, the heated air that's directed into the bottom of the furnace, and it's directed in through these nozzles, which are located around the bottom of the Bosch area of the furnace. That's called the bustle main, and that directs hot blast into the bottom of the furnace. And then you've got these braided metal flexes where coal is injected into the bottom of the furnace. And then on the right hand side, we've got this cross section of this coal lance, directing coal into the hot blast, and that tends to this tends to form a balloon-like void known as the raceway. And the raceway is where sometimes you've got enriched oxygen which is injected into the furnace, and this is where the temperature really ramps up and you get combustion or partial combustion takes place, and you get the generation. So you get heat generation, you get the production of carbon monoxide, which is the main reducing gas in the process. You also get production of a certain percentage of hydrogen depending on the type of coal that you're using as well. And the benefits of using this is it substitutes as a portion of the coke. And coke is produced by heating coal in an inert atmosphere, and it requires a lot of pre-processing. There's a lot of emissions associated with it. It's one of those things that you try to minimize, really. So coal injection improves this process efficiency, raises the heat, generates a reducing gas, and consequently, by improving the yield, it reduces CO2 emissions. But there are potential issues from it because of particulate emissions, which then hinder the gas, the gas permeability through that burden of raw materials, which I explained earlier in the countercurrent reactor. But in terms of energy, typically the type of additions that you put, the coal injection additions would be up to a couple of 100 kilograms per ton of hot metal. So for an output of 4 million tons, which would be typical of Port Talbot, we're talking about 600,000 tons of coal. And you substitute that about 0.95 kilograms of coke. So you avoid that coke production. So you reduce the emissions associated with it. And there's a significant energy saving. Best available technique data quantifies that at 3.76 gigajoules per ton of injecting coal. So it reduces the energy. There's an energy saving associated with it. Now, in the UK, Port Talbot uses granulated coal, but most worldwide coal injection is pulverized coal. Now that saves energy associated with its injection as well, because it requires less energy to mill that coal prior to injection into the furnace. Theoretical maximum is around 270 kilograms per ton of hot metal. So there's still some room for improving that, but you require a certain, in the blast furnace, you require a certain amount of coke, to allow this gas permeability, to allow the blast furnace to function as a countercurrent reactor with solid materials descending and gaseous materials ascending. So I've been using a drop tube furnace, and we use that to mimic this raceway region, this balloon-like bubble that's formed in the bottom of the furnace when you inject coals. And this gives characteristics which are similar to that raceway region: high heating rate, low residence times, high temperatures. And then these images are looking into this furnace and just illustrating that coal particulates, when they're injected in at high temperature, behave differently. On the left-hand side, you've got a more regular, symmetrical propagation of and combustion of materials. And then on the right-hand side, this granulated injection, higher particle sizes, tends to be more fragmented. You see this particle fragmentation. So what I'm suggesting is that, when coals are injected, they behave very differently. They burn out very differently, but they also produce, because they don't completely burn out, it's likely that these chars, these that are formed, then find their way into the blast furnace, and they exhibit different effects like fragmentation, swelling, and agglomeration. All things which are also very applicable to other particulate iron-making processes like Finex, for example, or Hysana. Surface, we've used X-ray photon electron spectroscopy to analyze the surface chemistry and then correlate that then with reactivity to try and improve that. And we've looked at the gasification reactivity of these partially burnt chars, because these partially burnt chars, there'll be insufficient oxygen to combust those further in the furnace, so they have to react by the Boudouard gasification reaction then to generate more carbon monoxide. And then this picture illustrates here the difference in the char volume. This is the same massive material. This is the coal, same massive coal and char. So the char can occupy a larger volume, and that has implications on the efficient utilization. So what I'm looking at more, what I've been looking at more recently, is the use of plastics and potentially biomass paper in reducing the CO2 emissions. And the importance of this is that potentially there's room to improve the CO2 emissions from plastics injection. So not only are you repurposing the blast furnace, not only are you utilizing material that otherwise might find its way into landfill, but you're also substituting, importantly, you're substituting mined coal. And in the process, you're improving the CO2 savings per ton of hot metal, per ton of plastic that's injected into the furnace. This is not something new, although I have been looking at a combined paper plastics product called Subcoal. Generally, blast furnace operators are either looking at biomass or biomass derived material, or they're looking at plastics. They're not looking at combined synergies that may be there from utilizing that type of material. But voestalpine use plastics injection in their furnaces. It's well established in the Japanese market. Japan adopted it primarily as a means of dealing with their waste plastic. And then I mentioned that my product Subcoal is a 50-50 paper plastics mix. So paper is derived, is biomass derived, isn't it? But some countries, for example, Brazil, which has a well-established sugar industry, and Scandinavia, which has a well-established forest industry, they're particularly interested in looking at the use of biomass as a means to reduce CO2 emissions from the blast furnace process, because they've got residues available potentially there. But it's getting those residues in there to realize the CO2 savings. And in particular, this Matheson has done some research looking at the use of or substitution of charcoal into the blast furnace, where quite significant savings of CO2 per ton of crude steel could be achieved. So demonstrated some important savings there. So there's options for the blast furnace process. In Japan, they're also looking at reconfiguring that process. So we have the conventional blast furnace represented here. A reason that the blast furnace utilizes a lot of energy is that it's a very high temperature process. So by substituting high reactivity coke, there's the potential to reduce the temperature of that process. So a low temperature blast furnace. Also then by either reducing gases such as coke oven gas or natural gas, reformed natural gas, that there's more potential to reduce emissions. Oxygen blast furnace or advanced oxygen blast furnace, top gas recycling, all ways to modify the blast furnace. And then on the right hand side, we've got a figure that illustrates the reduction in this coke rate, which is very important to, of course, there's a theoretical minimum then for that, but because of this requirement for the gas permeability. But some significant changes, some insignificant improvements in the coke rates associated with the blast furnace there. So this potential blast furnace in the evolution could, going from the conventional to the oxygen blast furnace, could also drive blast furnaces to perhaps be smaller, produce a more higher calorific gas that's more useful, and that can be converted to perhaps more useful byproducts as associated with the conventional blast furnace. So with higher concentrations of CO2, they're more readily separated, stored, or utilized. And potentially, when you think about it as well, if we're talking about hydrogen in the blast furnace, then hydrogen production by electrolysis would also generate oxygen. So it could perhaps be synergistic to this kind of development of a blast furnace to higher oxygen blast furnace. So there's quite a list of potential ways to reduce blast furnace energy and emissions, and quite significant savings associated with state-of-the-art power plant, coke dry quenching instead of the wet quenching that continues at the moment. A recent article in the Financial Times quoted ArcelorMittal, which is Europe's biggest steelmaker, and they've estimated that decarbonising its facility on the continent in line with the EU's drive to eliminate greenhouse gas emissions by 2050 will cost between 15 and 40 billion. So significant sums of money are going to be required to kind of rejiggle this industry. So options for reduced CO2 emissions. In the table, we can see the blast furnace with the basic oxygen furnace route for producing steel, between 1.6 and 2.2 tons of CO2 per ton of steel. And then top gas recycling brings that down, with carbon capture brings that down further. Then you've got direct reduced iron with the electric arc furnace, which brings it starts to bring it down further. And then when we start to consider hydrogen, we're bringing those CO2 emissions or specific CO2 emissions right down. So it's possible even with primary steel production to bring those emissions down. With secondary steel emissions, there's already significant opportunity to utilize those savings. And so we're talking about, in the blast furnace, we're talking about these innovative process modifications, top gas, oxygen, high oxygen, etc. If we increase the secondary manufacture from scrap use, then we've got associated emissions reductions with that. Biomass, carbon capture, hydrogen instead of the carbon monoxide as a reductant, and the use of alternative technology, direct reduced iron, hot briquetted iron, or low reduced iron as well. Or even electrolysis from molten iron oxide salts. So where are we in terms of the projections? Well, steel production is expected to rise to 2.8 billion tons by 2015. So large increases in the steel production. Also large increases are projected for the use of recycling from scrap. The International Energy Agency said that we've got to increase that use of scrap. The CO2 emissions are expected to reach, way above 3 billion tons if we don't do something about it and we don't repurpose this industry. And of course, the producers of steel, we see India is set to increase from its current share of about 5% to around 20% as well. So I mentioned hydrogen briefly. Of course, hydrogen really is a stellar potential to reduce CO2 emissions, and there are a couple of hydrogen projects which are in the pipeline at the moment in Austria and in Sweden, and there's significant potential to reduce the emissions of high iron production using this hydrogen-based route. A variety of different ways it can be incorporated into the blast furnace, but there's a limit to what you can put through the blast furnace, and then it can be incorporated at a much higher level than in a direct reduced iron to produce direct reduced iron, or potentially if it's used as the only gas in direct reduced iron production, it could be very high incorporation, and then associated CO2 emissions would be much lower. So the hydrogen in the blast furnace, although it reduces pressure drop in the blast furnace, which is beneficial because it's lighter and it's a less viscous gas compared to the carbon monoxide, the reduction of iron by hydrogen is endothermic, so it has a heat requirement. So it affects the heat balance, which limits the overall amount of hydrogen that you can put directly into a conventional blast furnace. There's also the issue about supplying of hydrogen. The current annual UK hydrogen production is around 24 million cubic meters per day. And for an output, if we were producing 4 million tons of steel per year, that would be 6.72 million cubic meters of hydrogen per day. So at 28% of the current UK capacity. And important in this consideration is how we produce that hydrogen as well, whether or not it's produced by methane reforming from fossil fuels, or whether we combine that reforming with carbon capture and storage to produce what's termed as a blue hydrogen product, or whether we're generating it by electrolysis. And I did some back of the envelope calculations, and green hydrogen production by electrolysis would require somewhere in the region of 14 terawatt hours per year. And the current UK solar generation is 13 terawatt hours per year. So there'd be some significant requirement to increase the hydrogen capacity. In terms of scrap-based steel making, it requires less energy and produces much less CO2. So it's got a lot going for it. We talked about the electric arc furnace, but other options that are being considered, this primary energy melter by ArcelorMittal is also being considered, and that's something that's readily available now. Particularly important, we export a great deal of our scrap, over 8 million tons a year. The global scrap market is set to treble. We can see the necessity to use more scrap, so there's significant opportunities there. But when it comes to competing, the UK needs to address things like the disparity in electricity price, and consequently the knock-on effect onto the final product price. And then there's issues of scrap contamination, and currently it's only used for, or tends to be used for lower quality end products. And then on the right hand side, you've got the figures there which kind of show our UK steel production going down and the emissions going down for the production, but our consumption emissions are increasing. So there's this necessity to really deal with this consumption as well. So now finally, I'm just going to go quickly over some of the options that are available and are being looked at in other countries. In Japan are technology leaders in iron and steel making. They've got the Japanese program is called Course 50. And they're looking at, it's still a blast furnace centered CO2 reduction, but this is through innovations in the blast furnace, carbon capture, increasing the amount of hydrogen used in the blast furnace, and energy savings as well. So I know your group at Warwick are looking at the Thyssen process with Tata Steel, and this is a really interesting smelter reduction technology. Some interesting interactions, gas solid, gas liquid, solid liquid interactions between particulates, which are very interesting from a scientifically point of view. The potential to reduce CO2 emissions by around 20, maybe more % but requires this carbon capture to really utilize big CO2 reductions. Thyssen Krupp in Germany have quite a well-established and clear vision. This arrow on the timeline for 2050 illustrates their projected evolution for their steel production, and from their 4 blast furnace setup here incorporating hydrogen, they aim to use direct reduced iron in conjunction with hydrogen production, and then more complete conversion to utilizing hydrogen, and then utilizing hydrogen for direct reduced iron into 2050. And then concurrently, they've got this carbon utilization program as well, where they're aiming to utilize carbon dioxide from the top gas. ArcelorMittal are really active in this field, and they're looking at all different aspects as well, quite diverse. That's kind of what's striking, really. You've got reduction using this plasma torch, where they're using natural gas dry reforming reaction. So you've got methane reacting with carbon dioxide to produce carbon monoxide, and hydrogen as reducing gases in the modified blast furnace with quite significant savings per ton of crude steel there. And then they're also looking at using the top gas with the Steelanol project in conjunction with LanzaTech, who are using the CO2 from the top gas by a biological fermentation, gas fermentation, conversion to bioethanol. And then we've got direct reduced iron, which which tends to go into the electric arc, predominantly goes into the electric arc furnace. Well-established technology, centered around countries that have a large natural gas resource, where they use, where they produce this sponge iron and product that goes into the electric arc furnace. And up to now, although these technologies have been scaled, they've got Midrex have got technologies that are capable of producing 2.5 million tons of liquid metal a year. Tons of steel per year when it's used in conjunction with the electric arc furnace. But as we've seen from the overall steel consumption, production and consumption worldwide, it's still dominated by the blast furnace. And then we've got some more novel opportunities in the form of electrolysis. Boston Metal Company, Sidowin, another one supported by ArcelorMittal. And then there's also an equivalent within the ultra low carbon steel making program in Europe too. So the World Economic Forum, International Energy Agency, World Steel are all driving towards and projecting a vision of decarbonisation, a pathway to 2050. It's interesting to see that they have mentioned demand management, but surely demand must be a big part of dealing with these emissions in the future. And then these worldwide decarbonisation programs that I've listed on the left there, the ore-based higher specific intensity carbon dioxide intensity processes, they're driving towards changes in evolution in the blast furnace, top gas recycling, oxygen blast furnace, using biomass, using carbon capture, using hydrogen to drive this CO2 produced per ton of steel. So the trend is from where we are currently with the worldwide average to utilize more scrap-based production and to move this down to a lower specific CO2 production per ton of hot metal. So the IEA roadmap set out that governments, key ways that this is likely to be achieved. Governments are going to have to help by providing R&D funding, creating this market for near zero emissions, adopting mandatory CO2 emissions reduction policy, and expanding this international cooperation, developing the infrastructure that's required. There's going to be a significant partnership, significant partnerships, collaborations that are going to be required to deliver this. And the current market activity suggests that multiple approaches are going to be the order of the day, really. They're going to fit policy, circumstances, resources, investment, social acceptance, and all the while, as well as this consumption and production of steel-based goods, a green economy is going to be supported by this steel production. So finally, when you consider the breadth of activity to reduce CO2 emissions from the iron and steel making in Europe and worldwide, I think it emphasizes just how necessary networks like Sustain are to cover what's going on. And there's a focus for activity in this sector. It's a really exciting time for iron and steel. And above all, I hope the industry is given a proper chance to be part of that solution, which takes account of the whole story that accounts for both our consumption and our production-based emissions, not just our production. So thank you very much for your attention. And I know I've probably gone over a little bit of time, but I hope you found it interesting, and I'll answer any questions.
Thank you, Julian. Please ask a question to Julian directly, and you can switch on your camera when you ask a question. Any question? Right. Okay, Ras, go ahead first.
Hi. it's a really fascinating presentation. Thank you. We've been looking at some of these, or starting to look at the increased use of scrap and how it could be, how more scrap could be used in the UK. One of my biggest questions is, do you have an opinion on which way you think the UK steel makers will go, particularly those with blast furnace processes, and in the next 10, 20 years? Because the sheer cost of reinvesting, of investing in steel processing to improve its CO2 is prohibitive in the UK for a whole list of reasons. And I just wondered if you have an opinion on which way they'll go.
Yeah, I kind of guessed that question had come up, and it's a really difficult one to answer, really. And I don't think, I couldn't really do it justice, to be honest, other than to say that it requires the government and industry coming together. It requires a vision. It requires something over and above what we've seen previously, that business as usual is not an option. And that if we use Europe and worldwide activity as any sort of example, then I think what we can see is that there's not a clear single solution. It's likely to be multiple solutions. I mean, the electric arc furnace is standout performer in terms of reducing our CO2 emissions, but we really need to be able to continue to be able to produce quality steels, which is what the UK does produce, a lot of quality steels, and so we need to continue that. Surely, that's going to be important, that we can kind of increase the amount. Ideally, we'd like to see investment and support for the industry, commitment to the industry to adopt some of the opportunities that there are in the current blast furnace configuration as well, and perhaps combining that with direct reduction or electric arc furnace. I mean, it requires almost fertile soil, really, and when you've got prohibitive electricity prices in the UK, then if you are looking for market mechanisms to drive this agenda, then I don't think that the UK is always going to be struggling to do that, and the UK, through fantastic technological developments and no small part to the skill and knowledge of its workforce, has been able to retain a presence despite these difficulties. So there's a lot of capability there. I'm guessing that the future is going to require those. It's going to require a lot of support, collaboration, creativity.
Thank you. I could talk to you about this for hours, literally hours.
Yeah, likewise.
Yeah, so answer everyone else's questions, and maybe I'll send you an email.
Carl, please go ahead.
Thanks a lot for that. I had two questions, and Russ very kindly asked one of them. So my other question is that you presented really a great host of potential future technologies for ironmaking. In terms of those, particularly thinking about sort of the plastics and such, is there anything that us people further downstream need to be starting to worry about in terms of different residuals that might be starting to make its way down the chain? Do we need to start preparing for that now, or is it much of a muchness? Obviously, when we started using more recycling, then we started to look at more copper and zinc and things. Is there anything else that we need to be starting to have a think about?
Well, I mean, the first thing that occurs to me is that, if we're going to electrify our transport sector, then we're going to see a lot different types of metals coming through into our scrap sector as well. So we've already had to deal with elements such as zinc when we increased the use of galvanized scrap, and I think this is an area that we potentially could see a lot more development in, really. Because it fits so neatly in with a circular economy, because we need to improve our recovery of these type of residuals. Also, you've got to consider that I think that the changing quality of the raw materials may find an influence or have an influence on the process and how the process adapts to deal with that. You know, one assumes that to produce a quality steel, the front end manufacturing will have to find ways to remove those residuals before it gets to the scrap. Whether or not that's the case is another matter. But you know, in the case of plastics, obviously there's potential for a number of materials to come through. Then that could affect things like slag volumes and co-products coming out of the primary steel making.
Yeah, that's exactly. Well, yeah, brilliant. Thank you very much for that.
Jusu, please.
Hi, Julia, thank you so much for your wonderful talk. My question probably is sort of follow up with Ross's question. So in this country, so the UK already set up the target by 2040 or 2050 net zero. And then we know the target, we know the end, and we know the other countries are doing. And then we are steel makers or a member of the steel community. If we look at the UK's situation, say we know the multiple options there. Which option you think is the most appropriate or for the UK?
Well, the electric arc furnace is an obvious option to increase the amount of scrap that we use in the UK, but if energy costs are high, then it might be difficult for us to, it might be difficult for the market alone to decide to make that choice.
Yeah, then how we can achieve that? Is the market decided? Is it?
Well, preferably,
yeah,
we need a government and market-based kind of the government and the market coming together to assist really and support the scales of investment that are going to be required. You know, steel making is going to be required for a green economy, so we should be supporting steel making. We've got to acknowledge that we consume a lot of steel, even if we ignored our production. If we said, oh, the simplest solution is for us to stop production of steel in the UK, we're still consuming a lot of steel, and surely we should be driving that agenda. We've got the skills, we've got the capability. We need that marketplace, and the government needs to assist in preparing the ground really for these new technologies to be adopted.
So what kind of government support you expect?
Well, I'm expecting the government to, it would require back-in investment, facilitating that investment. Not necessarily nationalization. That's probably less politically appealing. But I'm presuming that if you're going to require the industry to invest as well, you're going to require the industry. You're going to need to prepare some sort of policy certainty as well. So you've got to, with the policy, the industry needs to see that there's a policy that is going to support a particular route. Countries like Japan they've initiated, the government has initiated the Course 50 program, and it utilizes, it's a massive collaboration, both private, public, academic, all of that supports that vision. But then upping it to the investment is going to be another scale. And I don't, I guess the answer is I don't have a clear view,
okay.
so or clear solution for that. What I do realize is that for too long the industry has been left perhaps to its own devices. The market has been left to its own devices, and we have to recognize that if we're going to be serious about dealing with CO2 emissions, then surely we've got to back that up account for our consumption as well as our production of CO2 emissions, and back it up with some sort of vision.
Okay, thank you. So another question is a very small question. Is about in your presentations you talk about using the plastics, using waste carbon from other industries. You can save a large amount of carbon dioxide emission.
Yep.
I actually wanted to, can you explain how do you calculate the carbon dioxide reductions?
Well, the carbon dioxide emissions I've taken from other people's research.
Okay.
So, and there's a wide variety of that, and it's based on and it would be very dependent on the type of biomass that you're using, and it might not readily be a solution for all blast furnace operators, because you might not have that resource available. In Scandinavia, you have a strong forest industry that produces residual biomass in conjunction to that activity. In Brazil, you've got a strong sugar cane industry that produces a lot of sugarcane biomass bagasse that can be used. Then if you want to get it into a blast furnace, you've got to get it in a certain form. If you produce charcoal, then potentially you can utilize the gases from that production and then utilize the solid through injection. But I've taken life cycle analysis figures from multiple sources of research then, but I haven't calculated that myself.
Okay, because I saw like the Japanese, they have established plastic injection to blast furnace. They talk about they can reduce the carbon dioxide emission. I'm wondering if they actually include the burning of plastic will produce carbon dioxide or not. Do you think that part is counted as a reduction or not? Because if I think about it, if you inject plastics, you produce more or less a similar amount of carbon dioxide.
Yeah, well, yes, but you are substituting that carbon dioxide. You're also producing carbon monoxide. You're also producing hydrogen, because plastics have a higher hydrogen content. So you've got savings that are associated with those the hydrogen, and all the while that is substituting coal that you would have otherwise mined, transported, possibly converted to coke. And the emissions associated with those various steps and stages.
Thank you. I'll leave time to others to ask questions. Thank you.
Michael, please.
Thank you. Thanks for the very interesting talk. I just want to follow up on the discussion that Zushita started, because I find this interesting. When you use finely ground coal powder or plastics or a feedstock and these kind of things, do you think the energy requirement in order to produce that material and to grind it down to the desired powder size is actually significant and should be considered in that?
Yeah, it's certainly significant, and closer scrutiny of the life cycle analysis should show that. Related to, or in comparison to coal, you would have to do the same with coal as well. Whatever form of carbon you are putting in there, if you utilize plastic, you haven't got the coking process to deal with. You could potentially put plastics in with the coke as well. So there are potential options there, but that will affect coke strength. So yes, it should be accounted for. Plastics should require less milling than the coal. They tend to be produced, they tend to be softer. They tend to be lower temperature processes. So theoretically, it's what I'm saying is it's necessary to account for it. Yes, of course it is. But of course you'd have those associated milling costs with coal as well.
Okay, yeah. And do you expect any problems actually with the impurity levels if you use, say, products from the forest industry? Do you see this more a problem for the purification, or do you see this as a problem of an increased corrosion actually during steel processing?
No, it's a good point, and it's a real potential issue. Is because biomass tends to be higher in sodium and potassium in its ash and mineral composition, that could potentially be problematic in the blast furnace at higher levels, really. And those are things that already have to be considered with coals, actually, because depending on the quality of your coal, depending on the mineralogy of the ash, they will all affect your slag volumes, interactions, volatilization, cycling through the furnace itself. Biomass tends to have lower ash contents, but plastics tends to be more heterogeneous, and you've got problematic elements such as chlorine in there. So yes, and adopting a method that can take all, I think would require some sort of segregation, pre-processing possibly.
Okay, thanks a lot.
Ross, please, last question.
Yeah, sorry. There's been a discussion going on in the background for those of you viewing the chat. I just had a comment to make, which is when we were talking about electric arc furnaces and the lower CO2 emissions. The lower CO2 emissions are only true if you look at it as the electric arc furnace on a whole. If you're not using green energy for your electricity, then actually your CO2 emissions for the supply chain is still as high. So if we don't consider that, the argument has to be bigger than just how you're making the steel. It has to be an overall supply chain discussion at some point with regard to CO2 emissions. Otherwise, we're missing the big picture. It's why offshoring doesn't work, because if you offshore, then we just make the CO2 elsewhere and we still kill the planet. Anyway, sorry, that wasn't the question. The question is actually from Stuart Bradley, which is, what do you think of the future of the new coal mine in Cumbria? The motivation for the question coming from, do you consider it to be part of the overall steel energy mix, or do you think it's something that actually it's not a good argument for a coal mine, if you like?
Well, I don't know all of the details, but what the details I have seen then suggest that they've not guaranteed that all the production will go to UK plants, and a lot of it will be exported. And I guess when you look at it that way, it's perhaps not as appealing. Is the government prepared to back its other policy of reducing coal, as opposed to using the coke that's produced there? So that's highly politicized, I know. So I think because of that situation where a lot of the coke is still going to be exported, you're going to have to back it up. If you're going to say that we don't have to transport coke to UK blast furnaces, then we have to be honest about where the other stuff is going and what the emissions are associated with that transport.
Thank you.
Clive, do you have any questions?
As with a lot of people, I'm sure that there are plenty, but I think I need to get to my next meeting, but I think there'll be opportunity for me to talk to Julian another time. But I thoroughly enjoyed your presentation. I thought it was a lovely overview, and as you can hear, it's given a lot of stimulus for thought. And I think that there are sort of big picture questions of what would we like to have, and compromised answers of what in the current situation is likely to have.
Yeah, thank you.
Thank you, Julian, for a really wonderful talk. And really, I think everyone enjoyed it and lots of questions. So
Yeah. There are a lot of unanswered questions there, and there's a lot. There's a lot of uncertainty. I think the market. I think that the breadth of activity suggests that there's a lot of uncertainty which are the best routes.
Yeah, that's true. Yeah. I mean, but this discussion, I think it's a help, and it's a brainstorming for everyone to think about it.
Me too.
Yeah. Thank you, Julian. And
Thank you very much for having me.
Thank you.
Thank you very much indeed.
Thank you, Julian.
Thank you as well.
See you, everyone.
Amazing.
Yeah.
Bye-bye.
All right. Bye, everyone.
Bye.